Anatomy 32, Chapter 10, Muscular Tissue. Topics: Signals for a contraction. So, the nervous system is what controls the contractions of the skeletal muscle tissue, and of course, therefore, the skeletal muscles themselves. And the nervous system uses somatic motor neurons to send signals to the muscle fibers to signal the contraction. So what we see here in this image is an axon of a somatic motor neuron going down and making contact with a muscle fiber. And this place where you have the end of the axon adjacent to the muscle fiber is referred to as a neuromuscular junction. So neuro for neuron, muscular for muscle cell. So neuromuscular junction, where the end of the axon of the somatic motor neuron is adjacent to the muscle fiber. Now within the neuromuscular junction, we have, of course, the axon terminal, and we have part of the sarcolemma of the muscle fiber, and the nerve impulse, when it arrives, will travel down the axon to the axon terminal, but it cannot reach the muscle fiber directly. The reason for this is when we take a close look at the neuromuscular junction, we see that the very end of the axon terminal is a structure called a synaptic end-bulb. This is the very end of the axon. And then there's a space, and then we reach the muscle fiber, specifically a part of the sarcolemma called the motor end plate. So the motor end plate is the part of the sarcolemma that is a part of the neuromuscular junction. So again, we have the synaptic end bulb, we have a space called the synaptic cleft, and then we have the motor end plate of the muscle fiber. And so that nerve impulse cannot jump that space. Instead, what the nerve impulse is going to do is signal for the release of a neurotransmitter called acetylcholine. So within the synaptic end bulb are these synaptic vesicles, lots and lots of synaptic vesicles. And these synaptic vesicles are filled with the neurotransmitter called acetylcholine. So the nerve impulse arrives at the synaptic end bulb. This causes the opening of calcium ion channels, and calcium ions will flood into the synaptic end bulb, going from high concentration to low concentration. This arrival of calcium ions will then bind to the synaptic vesicles, causing them to begin exocytosis, causing them to travel to the surface of the synaptic end bulb and release acetylcholine into the synaptic cleft. So again, those calcium ions cause the synaptic vesicles to engage in exocytosis, to migrate to the surface of the synaptic end bulb and release the acetylcholine into the synaptic cleft. The acetylcholine can then diffuse across the synaptic cleft. When the acetylcholine reaches the motor end plate, it will bind to acetylcholine receptors. So there are these proteins, these transmembrane proteins attached and a part of the motor end plate. And acetylcholine can bind to these proteins, these acetylcholine receptors, causing these proteins to open up channels that allow sodium ions to flood into the muscle fiber. So acetylcholine binds to acetylcholine receptors on these channel proteins. Channel proteins open and sodium ions flood into the muscle fiber, going from high concentration to low concentration. Now, if enough of the acetylcholine receptors are bound to acetylcholine and enough of these channels open, there will be enough sodium ions entering the muscle fiber, leading to the generation of a muscle action potential. So if enough change in charge at the motor end plate occurs, because of sodium ions entering it, this will lead to a muscle action potential, which is a opening and closing of voltage-gated ion channels along the length of the sarcolemma, starting at the motor end plate and heading out the length of the muscle fiber. And eventually acetylcholine is broken down, and that'll end the signal, ending the muscle action potential. You don't contract forever. All right, so here is the motor end plate. And the motor end plate has a ton of acetylcholine bind to its receptors, leading to lots of sodium ions entering the cell, causing the inside of the cell to become positive, causing this significant change in charge at the motor end plate. This then causes neighboring voltage-gated receptors, voltage-gated channels to open. Ions then flood into this part of the neuron, changing the charge there. This then causes voltage-gated channels to open in the next part of the muscle fiber. Ions flood in, changing the charge, and so on down the length of the muscle fiber. So it's sort of like the wave at a stadium. The cheerleaders start at one side of the stadium, and as they're running across, people stand up and then sit back down. And then that wave moves along the length of the stadium. So it's the same idea, similar idea here. Muscle action plate has a change in charge from all the sodium ions entering. This causes voltage-gated channels in the neighboring region to open their channels, allowing ions to flood in, changing the charge, which then allows the next set of neighboring voltage-gated channels to open up, allowing ions to flood in and changing the charge, and so on down the length of the muscle fiber. And that is what the muscle action potential is. It is that movement of charge along the length of the sarcolemma. So the muscle action potential is the opening and closing of those voltage-gated channels that are causing a movement of charge along the length of the muscle fibers, sarcolemma. Now, when that muscle action potential reaches a transverse tubule, it will then travel down the transverse tubule, because again, the transverse tubule is just a continuation of the sarcolemma. When the muscle action potential reaches the triad, reaches that area where the transverse tubule is adjacent to the sarcoplasmic reticulum, this will cause the sarcoplasmic reticulum to release its calcium ions. So that change in charge brought to the sarcoplasmic reticula via the muscle action potential traveling down the transverse tubule, that change in charge triggers the release of calcium ions from the sarcoplasmic reticulum. And again, as I mentioned earlier, it's the release of calcium ions that triggers the shortening of the myofibrils. That then leads to the shortening of the muscle fibers, which leads, of course, to the shortening of the muscle organ itself. That's it for this part of the lecture.